When you think of weather, what comes to mind? Perhaps images of familiar weather patterns on Earth fill your thoughts. You probably picture rain, the gentle showers that nourish our planet, or sunshine, the warm, life-giving rays that brighten our days. But there's another kind, a type of weather that originates far beyond our atmosphere. It's space weather, and it's coming from our sun, the very star that sustains us. The sun constantly sends out, not just light and heat, but also a stream of charged particles called the solar wind, a continuous outflow that permeates our solar system. This solar wind relentlessly interacts with Earth, shaping our planet's environment in profound ways. Our planet is protected by a magnetic field, a natural defense system, an invisible shield that surrounds us, safeguarding life as we know it. This shield deflects most of these particles, preventing them from directly impacting our atmosphere. But sometimes the sun erupts with tremendous force, unleashing solar flares, sudden bursts of energy and radiation, or coronal mass ejections, massive expulsions of plasma and magnetic field from the sun's corona. These events send powerful bursts of energy toward us, traveling millions of miles through space. These solar storms can press against, compressing and distorting and even break through our magnetic shield, creating temporary openings in our planet's defenses. The result? Stunning auroras, the northern and southern lights dancing across the night sky, and more importantly, a direct impact on our technology, the very infrastructure that supports modern life. Satellites, which provide essential services like communication and navigation, communication networks, the backbone of our interconnected world, and power grids, the arteries that deliver electricity to our homes and businesses, are all vulnerable to space weather, susceptible to disruptions and damage from these solar events. That's why scientists are racing against time to understand and predict these solar events, developing advanced models and monitoring systems. By studying the sun's connection to Earth, unraveling the complex interactions between our star and our planet, we're not just exploring space, we're gaining critical knowledge to protect ourselves, we're protecting our way of life, ensuring the resilience of our technological society. Space weather forecasting, once a niche field, is becoming as vital as predicting hurricanes, a crucial component of our global safety and security. Space weather, driven by the sun's activity, can have a significant impact on our technology and infrastructure here on Earth. Understanding and predicting these events is crucial for protecting our satellites, power grids, and communication systems. To enhance our ability to forecast space weather with greater accuracy, NASA launched the Tandem Reconnection and Cusp Electrodynamics Reconnaissance Satellites, or tracers, a mission comprised of two small, yet highly sophisticated satellites designed to act as cosmic detectives, working in tandem to unravel the mysteries of our space environment. Their primary mission is to delve deep into the phenomenon of magnetic reconnection, a fundamental process that occurs throughout the universe. Specifically, tracers will study magnetic reconnection, the dynamic process that allows solar energy, carried by the solar wind, to penetrate and breach Earth's protective magnetic shield, the magnetosphere. Imagine two opposing magnetic field lines being forced together, then suddenly snapping and violently releasing immense amounts of energy. Tracers is uniquely positioned to fly directly through this action zone, providing unprecedented insights into the reconnection process. This groundbreaking mission, led by David Miles and his dedicated team at the University of Iowa, ultimately aims to answer critical questions surrounding exactly how and when this crucial energy transfer happens and what governs its efficiency. Before the advent of tracers, our understanding was limited to brief, often isolated snapshots of reconnection events gathered from single satellites. Now, with the innovative approach of two satellites flying in a coordinated formation, we are poised to gain a dynamic and far more detailed three-dimensional view of this complex process. The wealth of data collected by tracers and the insights gleaned from it will significantly improve the accuracy and reliability of our space weather models, ultimately helping us to better predict and proactively prepare for the potentially disruptive effects of solar storms. This isn't just an exercise in cool scientific discovery, it represents a practical and essential layer of protection for our increasingly technology-dependent world. The Tracers mission vividly demonstrates how strategically focused scientific endeavors can deliver substantial and far-reaching benefits to society as a whole. Tracers' journey began with a flawless launch from California aboard a SpaceX Falcon 9. The two satellites were deployed into polar orbit, ready to circle Earth every 90 minutes. Their high-speed path lets them frequently pass over the poles, prime spots for studying magnetic reconnection. The launch marked the start of a new era in space weather research. Years of planning and teamwork led to this moment of triumph. Now the satellites are sending back data, unlocking secrets about how the sun shapes our cosmic neighborhood. For NASA and its partners, this is just the beginning. The real discoveries are about to unfold. The genius of tracers is its two-satellite design. Flying seconds apart, they capture how space weather changes over time and space. It's like watching a wave move, not just seeing a single splash. Each satellite is packed with sensitive instruments to measure magnetic fields, electric fields, and solar wind particles. By comparing their data, scientists get a 3D, real-time view of magnetic reconnection. This tandem approach is a game-changer for understanding the Sun-Earth connection. For the first time, we can watch these explosive events unfold as a movie, not just a snapshot. The data will make our space weather models more accurate and reliable. It's a smart solution to a complex problem. Why all this effort? Because solar storms can disrupt our lives in big ways. A major storm can overload power grids, causing blackouts that last days or weeks. GPS and satellite communications can be thrown off, affecting everything from navigation to banking. Satellites themselves can be damaged or lost, costing millions. Astronauts in space face increased radiation risks during solar storms. Better forecasts mean we can warn power companies, satellite operators, and even airlines to take protective action. Just like hurricane warnings, solar storm alerts help us prepare and stay resilient. Tracers is a crucial step in building these early warning systems. Understanding the physics lets us safeguard our technology and society. The Tracers mission is specifically designed to target the polar cusps, those unique regions where Earth's magnetic field lines dip inward. These polar cusps act as magnetic funnels, providing a direct pathway for the solar wind to enter Earth's atmosphere with relative ease. It's like having a door slightly ajar in a fortress. These regions represent the weak spots in our planet's protective magnetic shield, making them particularly vulnerable to the constant barrage of solar particles. They are also the primary sites of magnetic reconnection, a dynamic process where magnetic field lines break and reconnect, releasing tremendous amounts of energy. This phenomenon is crucial to understanding space weather. Tracers stands out as the first mission meticulously designed to fly directly through these polar cusps. Its goal is to capture the magnetic reconnection process in unprecedented detail, providing a close-up view of this critical interaction. Equipped with its tandem satellites, flying in coordinated formation, it will reveal whether magnetic reconnection within the cusps is a steady, continuous process, or whether it occurs in explosive bursts, releasing energy in sudden, powerful events. Furthermore, tracers will shed light on how particles are accelerated and energized during these reconnection events, a key aspect of space weather dynamics. The wealth of data gathered will be like a Rosetta Stone for understanding space weather phenomena, translating complex solar activity into tangible, real-world effects that impact our technology and infrastructure. This mission represents the missing link, the crucial piece of the puzzle, in achieving a comprehensive understanding of the intricate ways in which the Sun and Earth constantly interact. By peeking into these magnetic funnels and observing the processes within, we're gathering the essential intelligence needed to develop next-generation space weather prediction capabilities, allowing us to better protect our assets in space and on the ground. Ultimately, tracers will fundamentally transform our understanding of our planet's dynamic relationship with the Sun and its place within the broader context of the solar system. Ultimately, Tracers is about creating a safer future for Earth and space exploration. The knowledge gained will help protect our technology, power grids, and satellites. With better forecasts, industries can take action before disaster strikes. As we send astronauts farther from Earth, accurate space weather predictions will be essential for their safety. Tracers is paving the way for safe, long-duration missions to the Moon, Mars, and beyond. This mission is a testament to human ingenuity and our drive to explore and protect. The two small satellites are on a grand quest, helping us weather cosmic storms here and among the stars. By looking up, we learn how to better care for our home. Tracers reminds us exploration and protection go hand in hand.